So good morning, everyone. Today I'm going to present the paper titled Life Gradient Compensation for Invading Straggler in the Distributed Learning. And this paper is published on the INFOCOM this year. And thank you for the author to provide the slides. And here is the outline. First, I will talk about the motivation, and then I will introduce their proposed method called the Life Gradient Compensate SJD, and then I will show the experiment results and finally conclude the paper. So this paper, they target on the scenario where we do the machine learning model training over a large scale data set. And using the distributed implementation can be benefit of handling the large data sets or reducing the training times. So figure shows the one of the standard architecture called the parameter servers, where we have the centralized servers and distributed different workers. So the worker will be assigned with different data partition and train the model locally. And then they will send the gradient to the server. The server will do the global average over the received gradient and then send back the model to the server, to the worker for further trainings. And within these distributed systems, due to the different capacity of different workers, the existing straggler issues, where it can cause the following factors. And actually, this straggler issue can be very severe. So this paper has already studied the different clients are jointly training the ChefNet. And as you can see, for different clients using different mobile device, either the computing time and the communication time can be very different. And the model aggregation time will be dependent on the system stragglers that can greatly slow down the model convergence. So to handle this system straggler problem, the existing literature has provided some of the solution. First approach is very simple. It's called the first K synchronized SJD, which in this paper they called KSJD. KSJD is only collect the gradient from the fattest K workers and discard the gradient from the straggler workers. So this way we can efficiently invading the straggler issues, but it can introduce the gradient or the sampling bias during the trainings. Since if we consider the straggler is not random but persistence, that means that we will ignore the information from certain workers, and that will degrade the model performance. And the second alternative approach is called the gradient coding. Here is the example from this ICML 2017 papers. The gradient coding actually just, instead of assigning single copies to different workers, the gradient coding actually can assign multiple copy to the worker so that it can guarantee as long as the server can receive the gradient information from any of the two workers, they can recover the gradient information about the overall data set so that it can improve the straggler tolerance or the node failure tolerance. But the disadvantage is also obvious that we introduce additional computing overhead and the memory storage to each worker. And in this paper, they try to address this drawback introduced by these two methods, and they're trying to find.
Rui, can you go back? Yeah, here. So the gradient coding here, this is a strategy to mitigate stragglers in federated learning or in distributed learning?
Distributed learning.
Right, it's not the federated learning, right?
Yeah, because the server would allocate the data to the worker.
Yeah. So how about the first one? I mean, the first key synchronized STD, they can be used for the federated learning, right?
Yes, yes. So it can use for the distributed and the federated learning way.
Yeah.
And
So
the second one, yeah.
Yeah, because I mean the gradient coding here, the federated learning here, the distributed learning, they have different challenges. The gradient coding here, I mean, if you are talking about the general distributed learning, the workers most of the time you can think they are homogeneous. It's not that important because you have a cluster, you have multiple machines. Perhaps the machine have same capability. That's very normal, right? So that they don't, perhaps, I mean, it's just in a cluster or in a data center. Perhaps that's the heterogeneity is not an issue. But in federated learning, you might, because the device are user device. So you cannot have, the same user device. So that's why you need, I mean, the gradient coding here, I heard about this tool, technical several times, but I finally found out that this is not used for federated learning, it's used just for the distributed learning in data center.
Yeah, yes. So even for data center, actually, in this paper, in this 2017 paper, they actually depict that even for the different cluster GPU, they also facing the straggler issues. Like their straggler issues is more like randomly because, for example, like when we facing the network bandwidth availability, that probably is dynamic. So sometimes the worker can be computed very slowly or transmit very slowly, so that it still exists in the straggler issue in the distributed learning. And using this kind of coding, I think they more helpful improving the node failure whenever the worker cannot send the gradient to the server, so that they can still recover the gradient information from the rest of the worker. They use the gradient coding. And yes, in this paper, because they target at the distributed learning way, it's not specifically for the federated learning issue. They list this related work here. Yeah.
Okay. But this paper, the paper that you are going to present here, they focus on federated learning, right? Or general distributed
learning.
So they consider a cluster of machines, different machines, they have different capability.
But I think their scenario is more like in the federated learning setting, but their algorithm look like a distributed one.
Yeah, we can see what kind of, in that technical, what kind of assumption do they make? If they assume, for example, if they assume that each node can access all the data, then that's a problem. That's not the federated learning. That's for distributed learning, I think.
Yeah, I think their data setting is more like in the federated learning way because they consider the non-ID settings.
Okay, I see.
So Ray, I want to quick follow up Dr. Guo's question. So is there a clear separation between, the assumption of learning and the assumption of, I would say, the problem setting of distributed learning? Or is there any kind of belongs to relationship? For example, say federated learning belongs to kind of distributed learning. Can you further clarify this?
I think the federated learning is like the subcategory of the distributed learning way. But here, because they actually consider like the data partition, because distributed way, you can partition the data to different workers, or you can partition the model to different workers to train the models. So I think federated learning just one of the distributed learning framework.
Yeah, that's my general understanding. But here, okay, yeah. You just relax the okay requirements for the distribution. Okay. Yeah.
Yeah.
Please move on. Thank you.
So, so to handle the two drawback, they proposed a new scheme to invading the straggler issues. And also they provide some theoretic analysis for their proposed method and illustrate a new trade-off between minimizing the training time and the convergence error. So next, I will introduce their proposed work. And first, we can see the system model for the distributed learning. And we have the learning objective function as follows. We assume the loss function is smooth, but non-convex. And this global loss function can be further decomposed to several sub-problems that can be solved on each worker. So each worker will own their local data sets that could be non-ID, similar as the federated learning settings. And here we have the local loss function that solves in each worker site. And the traditional or the standard ways to using the distributed SJD to train the model and to solve these objective functions. And so for the first step, the worker would calculate the gradient over the mini batch samples. And then they will send the gradient to the server. Server will do the aggregation over the received the gradient from all the user or just from the first K workers. And then they were using the gradient aggregation to update the model and send back to the server, send back to the workers. And here we can see, here we assume that the full participant SJD in these schemes, in this aggregation rules, we call this as the full SJD. We can see the straggler issues when doing the update. So the KSJD actually just to ignore the slowest nodes and only do the gradient update for the first two. And however, doing so, we introduced the gradient biased category at the equation 7. So we have the first term to represent the ignored gradient from the stragglers. And later in the theoretic analysis, we will show that to ignore this, ignore the gradient from the straggler would degrade the model accuracy. So there.
Can you go back to, so for the KSGD here, for example, you have 3 load and you just pick the first 2. So do you still, for example, here, do you consider a synchronized case or synchronized case here?
Synchronized case.
So even if you ignore the slowest one, you still consider a synchronized case, right?
Yes. Yes.
I think last time, we talk about, I think Pavel talked about the asynchronous case, right? So yes. For the asynchronous, it looks like they can address this bias issue, right? If you make some assumption.
Yes, yes.
Yeah, because you restrict yourself to the synchronous version, even if you just discard, ignore the kind of delayed gradient. I mean, of course, you will have a bias issue.
Yeah, yeah. I think they particularly focus on the synchronized settings.
Okay. Okay.
So what they're doing is that instead of just ignoring the gradient from the straggler, they can put the straggler's gradient in the future round to update and do the bias compensations. So we can see here is our here's our gradient collected from the first K users. And when we do the next round updates, actually we were compensate this error by introducing the gradient for the next round and do the model update at t+2 iterations so that we can introduce the gradient of the straggler in the training process to reduce the gradient bias.
So is it a build the synchronized case? I mean, this one is kind of, you know, a modified version of synchronized case, more tending to asynchronized case, right?
Yeah, I think because they assume like transmitting or sending the gradient can be overlapping with the next round computing. So that you just using the gradient, delayed gradient to the next round to do the updates.
Well, let me change my question a little bit. So what's the difference between this one and asynchronized case? So you still set up probably a threshold, say, for example, XT, the blue one, you can only submit within the next round. You cannot submit that probably in XT+2 round.
Yes. I think they only consider one step delay.
Okay, that's the difference from the asynchronized case. Asynchronized case, basically, you can submit whenever you want, right?
Mm-hmm.
Okay.
Yeah, they can only consider like one step delay.
So do they compare this one with the asynchronous case and show certain kind of advantage of that?
No, they do not consider they do not compare with the asynchronous.
Well, then that's a problem. How can you show your advantage? You know, you abuse the synchronous case assumption, and you know, you don't compare with the asynchronous case. I mean, you don't compare with the extreme two ends. One is the synchronized case with Straggler, the other asynchronous case, right? Supposedly, you should compare with both.
I think they still consider it as the synchronized case.
But it's obviously, you know, it's kind of against the synchronized case rules, right? So that's the reason why I said if you do something like this, is something in the middle between the synchronized case and asynchronized case, right? So if you want to show the advantage of your proposed approach, you need to compare at least with the two extreme ends. One is purely synchronized, one is purely asynchronized. But I'm just trying to ask, you know, I know it's their paper, but I just try to ask, do they do this kind of comparison?
No, they only compare with the full SJD and the KSJD.
Okay. Yeah, please move on. I'll leave the opportunity to the other students, and you know, probably we can further check this paper.
Yeah. Okay. So in particular,
yeah. Can you just a follow-up question for them? So for this one, do they think for this here they so the server first receive the first two gradient, they do an average, and then they broadcast to everyone, right?
Yeah.
And then I assume that the device workers 3 are still working on the gradient in this mode at this time, right? So
I will introduce the detail in the next slides.
Oh, okay. So that's their design, right? That's
yeah. So just the idea that's showing that we can compensate to the next iterations. Actually,
okay.
We'll show the details. Yeah. So in particular, for the stragglers at each iterations, the straggler will continue to computing their gradient in the local, and the other nodes, once they finish their mini batch gradient, they can send to the servers. So the server can do the aggregation, and in the meantime, the straggler will keep computing their local gradients. Either they can complete the mini batch gradient showing as here. Once they complete, they can send to the server. The server will use this for the next round, or they can compute until they receive the new model update at this point. And in this point, they will send their complete gradient calculation to the server and ignore the rest of the incomplete work. So they can accept the partial work from the Straggler nodes. And to measure the partial work of the Straggler, they further divided the mini batch sample into multiple blocks so that they can measure how many works have done by the Stragglers. So the delay gradient actually can be characterized in the following way. We assume that this mini batch is unbiased estimation, and also the variance using the standard assumption, we can see the partial work here can be actually bounded in these terms. So the S here assume the total block of this mini batch data samples, and the R is the blocks that have been complete by the Straggler. So you can see the partial work actually has the larger variance when they send to the server. And to deal with this enlarged coefficient, they're actually using the linear scale down to reduce this value and send to the server to do the model updates. So is that clear?
So do you mean like the Stragglers are still sending their updates earlier to the server?
So there are two criteria. Once they can complete their mini batch gradient, they can send to the server once they complete. And the second one is once they receive the new updates, they will send their already complete gradient to the server. So it's only the partial gradient. So this is the time steps that determine whether they should send the gradient or not.
So it's like for the Straggler, what they do is like they don't send out their calculation results to the server, but they are going to update based on the server's global update. Is that what you're trying to say here?
No, they will send the gradient to the server, and they will continue. They will do the next round trainings in the same time using.
Yeah, I mean here, for example, for here. So obviously, because the straggling, they don't send it to the server at this moment, right?
Yeah.
And so, but they are still waiting for the global updates, and while they are continuing calculating. So at this point, at this point that they got the global update?
At this point,
okay, at this point they got the global update, and so.
Yes, they will send the.
They send the incomplete version of gradient updates at this point.
Yeah, they only send this highlight point here to the servers, and they ignore the rest of the computing.
But for this, what's the difference between the blue one and the green one? I think the green one do the same thing, right?
Yeah, green one is show the new.
No. The boxed green one.
Yeah.
At the bottom.
Same. I mean, they only send the gradient of here. They just ignore this blue dot one.
How about the green one? The last row. The last row.
Yeah, this one and this one seems to be different, right? What are the difference?
Yeah, I think these are just two types. The first one, the blue one, is just it is kind of really slow, and after as long as it received the global update, as long as it can receive the global update, and it just stop and send the partial gradient to the next iteration. Am I correct?
Yes.
Right?
Yes.
Yeah, and also for the green part, it is another type because it can finish the calculation before the global update received. So in this case, they can send all gradient to the next iterations. I think these are just the two types.
Oh,
Yes, yes.
But I think, I kind of get Xinya's point here. But what do they, for example, here, right? When you, let me try to, assume that you arrive here. So I assume that this worker, and this worker, they have finished their gradient calculation. They send it to the parameter server. Server do averaging and then broadcast to all the workers again, right? So everyone just start to work on the mini batch gradient again. However, for this worker, they have some unfinished work from the previous iteration, right?
Mhm.
So I assume that this worker, they should still work on this the previous iterations gradient first, and then they can receive a new model update, the global model, and then do the next iterations gradient again, right? So what happened here? I mean, for example, here you just assume that you take into account those partial gradient, but you didn't include it into the global model update in this particular iteration, right?
Yeah.
So what
Yeah,
did you do?
that's my question as well. So in this case, it seemed like the straggler would, I just don't see how the contribution of the iteration T of the straggler is being integrated into the iteration T+1. So are you going to introduce that later, or it's, so how does this part, like this part, being integrated to the global update? Like for the rest, they are going to update based on the global update, right?
Yeah.
But for this one, do they have the same starting point of the global update? If so, how do they integrate their previous gradient here?
The previous gradient will be sent to this point. So they will
You mean they just keep it?
here.
Oh, okay.
Yeah.
Okay.
but the
So
thing, but the sense is for the third line, right? So for the T+1 round, it continues training, right? So for that device or for that user, for T+1 round of global aggregation, is it going to contribute to two gradients? One gradient from the last round and one gradient from this round?
No. They can I erase this?
Yeah, sure.
Yeah, maybe we can just get some.
Yeah, I think this is in the Zoom, so it's not. I think someone need to erase that, or Dr. Gong, or
Not me. I have cleared all my annotation. So maybe.
Let me see.
Yeah,
No,
maybe it's
Oh yeah. Not that.
So actually, I'm sorry, what is the question again?
The question is for the user in line 3, right?
Here.
For T+1 round.
Yeah.
T+1 round. Line 3 is not line 4, line 3. T+1.
Oh, here.
Yeah. He's going to contribute one gradient from iteration T, right? But at the same time, for T+1 iteration, it continues training. So just imagine it finished training before the deadline. So is this, line 3 user is going to contribute another gradients to the global aggregation?
No, actually, the stragglers gradient will not contribute to the iteration T+1, but this gradient will contribute in the T+.
Yeah,
I think Dr. Pan's question is basically here. Like you see, there is a contribution here, a contribution here. Do you mean like the third and the straggler are contributing both?
Yes.
For this aggregation or this one?
So,
this one.
So one user is going to contribute to two gradients, right? So one is for this T+1 round, one is from the T round.
Yes, yes.
Okay.
So this worker, this worker 3, they will contribute 5 gradient, right? This is because this is the current 3 gradient. This is the previous 2 gradient. So they send the 5 gradient to the sulfur, right? In this iteration, is that? Oh yeah. Okay.
Yes, yes.
So similarly for this one, because it has a straggler issue, so these 3 gradient will not be used for this global model, but they will be used in the next iteration T+2, right?
Yes, yes.
Okay, I get the point.
Yeah, please continue then.
Okay, so yes, in that case, we can characterize the partial work from the stragglers. And here is the overall algorithms. So the user would first partition the mini batch size and do the local trainings. And so for the server, not only they will collect the fattest K fresh gradient at the current iteration, but also they will aggregate the delay gradient from the previous one. As here, they calculate the the bias and update to the global models.
Ray, could you go to previous slides? For this scaling part, right? I think it's proportional to how many mini batch training you finished, how many gradients you finished over the, for example, previous setting up like S blocks, right?
Yes.
So does that it is always proportional? Because probably different users, they have different data diversity, right? So it's not only related to the size, probably it's more related to the data diversity as well. So is there any paper discussing something like this?
What do you mean by data diversity?
For example, your data is more homogeneous, right? For example, my data is more diverse, contain more information for training. Even with the same data size we have, even same mini batch size we have, but I can contribute more to the training, but you contribute less to the training. Right?
Yeah.
So is there any paper design something like this instead of just using very simple proportional scaling law or coefficient?
I think there are papers talking about how to assign the weighting strategies to different workers. Say if their contribution is more, they can assign more weight. You do the weighted summation in the aggregation part.
But this one, they just assume their data is kind of equal to each other. It only depends on how many.
Yeah, they're just doing this very simple average.
Okay.
Yes.
Yeah, please continue.
Yeah, and here is the overall, the overall algorithm here. And next, I will introduce their theoretic analysis. Here, just listing the assumption they use in the convergence analysis, which is pretty standard. We assume the L smooth and the unbiased local gradients and the bounded variance. Also, they introduce the last inequality to characterize the non-IID level between the users and the global models here. The aggregated gradient here. So they first show the drawback of using the KSJD, which we only consider the first K users. So when we consider like the IID case, when the beta here equals to 0, we can see that their convergence, their convergence error it's depending on this learning rate. So if we can set an arbitrary small value of this learning rate, we can well control the convergence errors in the IID case. So they have the similar convergence rate at the full SJD. However, if we consider the non-IID case with the persistent straggler, the persistent straggler will be more in practice, like in the federated learning way, where we have different mobile device. So using the mobile phone or TX2 probably has the slowest computing time compared with the powerful GPU or the GPU clusters. So it probably has this persistent stragglers will be computing very slowly over several iterations. So ignore their gradient will cause the huge gradient bias. And you can see from the convergence result, they introduced additional constant terms that can result in the very high training errors. And however, compared with the KSJD, the proposed method used to compensate the gradient can receive the small convergence error by choosing the proper the proper learning rate here. So it shows that the proposed method can be performed better compared with the KSJD. And moreover, with proper learning rates, they can receive the convergence rate similar to the full SJD.
But you know, I think you know, even for the KSGD with persistent straggler, you can do a random sampling. You know, even for you have a persistent straggler, why do you here? I mean, there are assumptions that for the KSGD you rely on you always the server always just receive the K fastest worker. But in reality, what we do is that we say, okay, because I know there's some persistent straggler, right? So I perhaps just every time I randomly choose a subset of workers. So in this case, I can still utilize the data set from all workers, even if some of them they belong to the persistent straggler.
But you cannot use them all, right? But LGC, SJD, potentially they can use them all.
Yeah.
Even you do the random sampling, for example, you sample M from N users, right? And from this M user, you choose the K, top K. But the thing is, the M users you sampled, it doesn't matter you sample whatever. If there's a really persistent straggler, they're always the slowest, you know, in whatever sample set, right? So it's still there's kind of bias. You can never ever use their data or use their contribution. But for LGC, yeah.
I know what you mean. So so you say, for example, you have in total you have 10 devices. 2 devices they are persistent straggler. But doesn't matter because every time our random sample 5. Yeah. So this round I utilize 5, next round I use another 5. So finally, because you see the result here, the result are more like convergence analysis. It's not like a running time analysis. It's just a convergence analysis. So the reason why this one outperformed the LG-SGD, outperformed the KSGD is just because LGC-SGD, they can utilize all the workers' data. But KSGD, they can only use the fastest workers. So that's why they have in terms of performance, the convergence analysis, this one is better than this one.
That's true, but I'm not talking about the convergence analysis here. Probably for their convergence analysis, the KSGD, they didn't consider the random sampling subset approach you mentioned. But what I'm talking about is the general case, right? For example, the example you gave. for 10 users, 10 equals to n equals to 10, right? You have a two slowest user, right? For example, the k here, we select, for example, k equals to 2, right? Every time you subsample, say m equal to 5, you subsample, 5 users and choose the top 2 or top 3 for contribution. You can never ever choose the two slowest one.
Yeah. I mean, I don't. So every time I randomly choose 5, I will utilize 5. I will not just wait. I will not use the k fastest again.
Oh, okay. But
Yeah, but the time will be slow.
Yeah, the time will be slow.
Yeah, that's what I'm saying. Because I mean, so in terms of convergence analysis, I don't see big difference. But maybe in terms of running time, there will be some difference. But do they show the running time?
Yes.
Okay.
Yeah. So actually they have some discussion about how to select this threshold, and to discuss this threshold, introduce the trade-off between the per iteration computing time and the convergence analysis, the convergence error here. So for the analysis, they assume that the computational time denoted as the random variable x, and so they assume the random variable is ID across the multiple iteration and across all the workers. And so you can rewrite this expectation number of the iteration t by replacing with this equation. I'm sorry. So the small t here represents the total training time budget, and the mu k here represents the average computing time when we select the first k user, the fastest k users. And the tau here is the average communication time. So you can actually rewrite their convergence analysis into equation 18. And by taking the first derivative and setting it to 0, we can get this optimal selection of this k, which represents as p, the k over n, the selection ratio here. And as you can see, this optimal value is unique. And also, they dependent on several parameters. For example, if we consider the IID case where the beta equals to 0, or we have a very small time budget, that's the optimal selection of the k will be increased. And also, because the probability also related to the objective value during the training time, so that if this fx get closer to the optimal value of f stars, then we can gradually increase the selection of k, so that it will imply a future design for the adaptive strategy to adaptively increase the participant workers during the training time.
Those things are the bounds, right? So
yeah, this is the bound. They only talk about the possible strategies that may be influenced by different parameters here. So they do not give the specific the optimal policy for this case. They just analysis this one.
Yeah, but if you claim that's optimal selection of k according to a bound derivation, that can be a problem. Even you impose this kind of adaptive strategy is not necessarily better. Say I fix the k to be a certain number, right? Because your conclusion is come from the bounds.
Yeah.
Okay.
Yeah, it's just a small discussion, and the guidance say that the selection of k can be adaptive depending on the training process here.
Yeah, please move on. Thank you.
Yeah, and the next I will show the experiment result. First, here is the simulation setup. they consider the non-ID case where each worker will assign 4 C classes among the 10 total classes, since they consider the the CIFAR 10 dataset. And the model they use is the VGG net 11s. And in the experiment, they consider total 10 workers, and the first K equal to 7s. And also they simulate the straggler period that every H iteration, we will select 1 stragglers, and to keep this worker be the straggler over H iterations. So we can guarantee the straggler is random and independent. And here is their performance evaluation. They evaluate with different straggler periods. H equals to 1, which means that we will randomly select the straggler every iterations. So here the straggler will be randomly and independently, and the straggler period H equal to 150, which can be implied for the persistent straggler issues. So from the figure, you can see that they actually can be robust to the straggler problem and the non-ID problems. They have the similar test accuracy compared with the full partitions. And for the KSJDs, when the data is highly diverse, they cannot train the model to converge the points. So, yeah.
So full SGD is always the best in terms of testing accuracy, right?
Yes, because they consider all the workers.
But it's slow, right?
Yes, it's slow. So in the next slide, you can see in terms of the convergence round, the proposed method have the similar convergence round compared with the full SGD. But within the training times, we can see that the full SGD has the longest training time, while the proposed method can save over 35% of the time here.
Mm-hmm.
But they are calculating the training time based on a simulation, not based on like the running on the real distributed servers, right?
Yeah, because they simulate this time based on this distribution, the shifted exponential distribution here.
Okay.
And the next day,
so how do they determine the so the simulation per iteration time? Is this for the
computing?
I guess for the KSGD and full SGD, they should be different, right? Because that's the key reason that these two have different. That's the key difference, that they are different in the figure B, right? So for the per iteration time, is like per local iteration?
Yeah, per local iterations. You mean here?
Yeah, my question is like, so here they obviously can see like the per iteration time, the time per iteration for the full SGD is longer than for KSGD, right?
Yeah.
That's why you convert from figure A to figure B. So my question is like, for this simulation per iteration time, is that for KSGD or for full SGD, or is for something else?
No, I think it's a sample from the distribution, right? So XI belong to this kind of distribution. Is that true, right?
Yeah, they come from the
distribution. The EX.
So the X is just the sample of this the distribution here, and you use this to calculate the overall time.
So XI is more like the worker I's delay, right?
Yeah.
Yeah.
So
Oh,
one
okay.
one worker's delay. So because you have 10 workers, you will simulate well at this particular iteration, what's the worker time distribution?
Okay, I got
That's
it.
true. That's true.
Yeah.
Yeah. Okay.
Yeah, that makes sense.
Mhm.
Sorry. And yeah, they also talk about the trade-off between the of selecting different K. So the color here represent the different value of the K here. As you can see, while the K is increased, we can achieve the much smaller training loss, but the time has also increased as well. So compared with the KSJD, the proposed method can always achieve the better trade-off between the training loss and the training time here. Yes. And next they just do the
Ray, can you just go? So, how do they get, for example, just for, let's say just for KSGD, for each point, how do they obtain that? They just choose a different K and then they run the simulation.
so
Then
they set this K to be a fixed value, like 0.7 for N.
okay. So, so they set a K to a specific value, then they run the simulation until it
Yeah.
converges.
Yes, yes.
So does that mean that, for example, for some K, even I mean for example, for some K in LGC SGD, for example, this one they will converge, or they give you the minimum. This one they give you the minimum testing accuracy. But for this one, even if you choose the K equal to 6, it will not converge to the optimal solution, even for LGC SGD. I mean, here, so the minimum accuracy is here, right? So for other, so this is 1K, assume that 1K equal to 8.
Oh,
But this one, I mean, is more like K equal to 5. So when K equal to 5, they will level achieve the minimum accuracy.
yeah, because they fix the training iteration here.
Okay. They just assume that I have a fixed training iteration.
Yeah.
Why you want to fix training iteration? You should fix the training time, right? Or you give the same training time. You will say K when you select different K, they will give you different training nodes.
Here they just trying to show the trade-off here by fixing the training iteration. You can see the trade-off between the training loss and the training time.
If you fix the training iteration, when K is larger, the performance should be the best,
Better.
right?
Yeah, but the time will be longer.
Oh, okay. But you say here this performance is worse than this one, right? Even if your K is larger, it's still worse than this one.
The training losses, but the number here shows the testing accuracy actually is better.
Oh, so this is the
This is just the training loss.
so training loss. Oh, okay. So
Yeah.
this is the testing accuracy. This is the training loss, right?
Yes.
Oh, okay. Oh, I see. Okay.
By the way, I think this figure give us another, good suggestion is that we can represent multiple dimension information by use this kind of a Hating bar and other things, like this picture contains probably 3-dimensional, 4-dimensional information. So in the future, in your paper, probably you should refer to this approach.
Yeah.
Yeah, I agree. Yeah.
And yeah, they also testing the scalabilities by increasing the total number of participant workers. And as you can see, their testing accuracy compared with the full SJD is always the similar as the full SJD1 and can greatly reduce the training times. So, so in this paper, they provide this live gradient compensation framework to mitigate the straggler issues. And the experiment results show that they can robust to the non-ID dataset and the persistence of the straggler period. And yeah, they talk about the future work. Probably they can develop some strategy to dynamically adjust their user selections, the number of participants, the faster K users, or the block for the mini batch data samples. So that's it. Thank you.